On a routine flight between Helsinki and Tartu, a pilot glanced at his navigation instruments and felt a sudden cold wave of disbelief wash over him. The plane, which should have been coasting over the Baltic Sea, was inexplicably thousands of miles off course, hovering above a remote stretch of the Pacific Ocean on the opposite side of the world. Now this sounds like the opening to Lost. The reality is something much more scary. Russians. Specifically, a concerted body of activity to disrupt the way we navigate around our planet using the Global Navigation Satellite System, or GNSS, to provide GPS data. In fact, we can actually see this happening. This is the global survey activity that measures GPS threats and interference around the world. As we pan east, we notice a significant increase in the failure rate of GPS fidelity, with particularly high compromise exactly on the Helsinki-Tartu flight path. By assuming that line of sight is needed for this GPS attack and looking at the signal strength in the area, internet sleuths narrowed down the likely source of this phenomena to just west of St. Petersburg. There's also another interesting dead zone, but that one's located in the USA, just west of San Antonio. What initially got me interested in this story was videos like this one, that have been circulating the internet for a while now and show in the middle of a drone show hundreds of drones suddenly falling out of the sky. There was an internet rabbit hole that I went down that other drone companies were using GPS jammers to sabotage their competition. But all this brings me to one point. In a world where our main means of navigation, both military and civilian, is so easily compromised, what do we do about it? I wanted to find out, so I reached out to a team of quantum physicists and engineers based in Oxford that are working on a solution: the world's first quantum positioning system. A system that taps into the very nature of quantum mechanics in order to navigate. We hear a lot online, and you guys leave me a lot of comments, that the promise of quantum, much like fusion, always seems 30 years away. This is a direct counterpoint to that argument. The magic behind their technique comes from the ability to control ultra-cold states of matter.
At Inflection, we're experts in cooling and trapping atoms and manipulating them using magnetic fields and light. And the reason that we do that is that if you cool down atoms exquisitely cold, few billionths of a degree above absolute zero, then you can create a new state of matter called a Bose-Einstein condensate.
What Inflection are trying to do is develop a new approach to position sensing. But what exactly does that mean? When we think about working out where we are on the planet, there are really two main ways of doing this. Either trilateration, which is used by GPS systems, where we have a constellation of GPS satellites in orbit, constantly sending out their position in the sky and the time on their local clocks. These radio signals travel outward at the speed of light from each satellite, and if you detect a GPS signal, you can look at your current time, subtract the time of the GPS signal, and this tells you how long it took for that GPS signal to arrive to you. As all light waves move at the speed of light multiplied by this time difference tells you how far away the satellite is from you. You now know the distance, you just don't know the direction to this satellite. But if you can do this for 3 or more satellites, you can get a ring of overlapping possible positions that converges on a single point on the planet, telling you where you are.
But actually, GPS can be very easily spoofed and can be very easily jammed. So what I mean by jammed is it can happen for natural reasons. I'm in between large buildings, or I'm in a mountainous region, or maybe I'm under the ground, right? I'm on the tube traveling around London. I'm not going to get a GPS signal. GPS can also be jammed with very cheap jammers that literally block the GPS signal. Spoofed is a little bit more insidious, where you look at your GPS signal, it tells you that you're in one place, you're really in another.
That can be either in the theatre of war, or like a few delivery drivers did a few years ago to disguise the fact they were taking naps throughout the day. If that is the case, then all of these break the reliability of GPS.
If that goes down, you have to rely on something called dead reckoning. And dead reckoning is based on accelerometers, rotation sensors that measure inertial forces.
Dead reckoning was originally developed by sailors as early as the 1600s, trying to navigate around the globe. Back then, all they had was a compass, and that gives you a direction, but not a position. So how do you work out where you are? Imagine you are a sailor trying to make your way over to America. You start by locating your position on the map by looking for the port you are leaving from. You decide to head to America by moving straight west. If we make the physicist's assumption that ocean currents and stray winds don't knock us off course at all, and we follow our compass reading perfectly, where we are on the map is a simple question of how long we've been travelling multiplied by our speed. Sailors determined a ship's speed by throwing a log with a rope tied to it overboard. Every 47 feet a knot was tied in the rope, and by counting how many knots were pulled out by the log, the ship could determine how fast it was moving. This gave us the definition of speed measured in knots, still used by ships and aircraft to this day. This worked okay for sailors back then, but for some reason never caught on with commercial aircraft pilots. Maybe because you need a lot more rope, but also because these systems weren't accurate enough and velocity is rarely constant. So during the mid-20th century, particularly during World War II, dead reckoning systems moved to measuring acceleration rather than velocity. These worked broadly the same, but measured acceleration over time to calculate velocity, then velocity over time to calculate position. I like to think of this as basically what you do if you ever find yourself kidnapped and put in the back of a trunk. You feel the movements of the car around you and keep track of your position. This process works because every action has an equal and opposite reaction. To understand this better, you might imagine Einstein in a rocket ship in space. As the rocket accelerates, he gets pushed to the bottom of the ship. Similarly, moving left or right causes him to bump into the opposite wall. The device that measures all of these movements is called an inertial measurement unit, or an IMU, and it measures changes in acceleration or deceleration by watching its internal Einstein bump around. But why is this so interesting? It means that unlike GPS, no external reference signal is needed, which could otherwise be vulnerable to hacking, jamming, or spoofing. Dead reckoning systems just need to know where they started, and they can use the laws of the universe to determine the rest. They are effectively unhackable, assuming at least that no one has direct access to the device.
An elegant solution for keeping track of reality.
The problem with normal IMUs is that their sensitivity is limited.
And the reason for that is that all of these sensors have an unavoidable level of drift and noise, and that drift and noise accumulates over time. So you start off with your known position and you integrate forwards your local acceleration and rotation for a few minutes, a few hours, and a few days, and eventually the uncertainty of your position grows and grows and grows until it's no longer usable. So if imagine you're a submarine, you're trying to go from the middle of the ocean through a narrow straits or a channel gap without broadcasting your position with sonar or any emissive technology, you then are more and more uncertain about your ability to navigate underwater. And I pick underwater because GPS does not penetrate underwater at all. So regardless of the situation, you always need inertial navigation underwater.
The goal for Inflection is to overcome the limitations of traditional inertial measurement systems by developing one based on the quantum properties of the universe and a state of matter called a Bose-Einstein condensate. Because I'm an experimental physicist and I like understanding how things actually work, I wanted to see deep within their system to see how the pieces of this puzzle come together. To do that though, the first challenge is to make some of the coldest atoms in the universe. Can you start by just talking me through how you actually go about cooling an atom using a laser? Because that sounds utterly counterintuitive, you know, like usually you think of lasers as heating things up.
Yeah,
so how do you
lasers
actually
heat
use
things,
a laser to cool something down?
So the basic concept is when the photon of light comes in and interacts with the atom, it sort of stays momentarily with the atom and then is re-emitted into the environment randomly in all directions. And because every time an atom experiences an interaction with the laser light, it loses a little bit of energy, its kinetic energy is slowly sapped away as it interacts with many, many photons from the beams. And this happens in a way which opposes motion. So if the atom moves towards the laser beam, it scatters more light than if it's moving away from the laser beam.
This phenomena has been known for a while, but I always find it amazing. It's called Doppler cooling. As you might expect from the name, it exploits the Doppler effect, which is the change in frequency or wavelength of any wave perceived by an observer moving relative to the source. You're probably reasonably familiar with this in the example of a car moving towards you. As it moves towards you, its engine sounds like it's at a higher pitch or higher frequency than when it passes you and starts moving away. The same thing happens though with light. Atoms are exposed to a laser light that is slightly redshifted, meaning that its frequency is slightly lower than the natural frequency that the atom wants to absorb. The atom's thermal motion is random in nature as it bumps into other nearby atoms, but when it moves towards the laser light, the Doppler effect causes the light to appear slightly blue shifted, bringing the light's frequency closer to the atom's natural absorption frequency. gravity, and making it easier for the atom to absorb the light. Upon absorbing the photon, the atom experiences a recoil in the opposite direction to its motion, slightly reducing its speed. After absorbing the photon, the atom will eventually re-emit the photon in a random direction. This process is repeated millions of times, with the atom absorbing photons from the laser light and losing a little bit more speed in each interaction. If lasers are applied from all 6 directions, this can slow down the atom essentially to a dead stop.
Now that will slow the atoms down, but it won't trap them. So what we also add is a magnetic field, and that adds a restoring force, so the atoms are sucked into the center of the magnetic field. In this setup, we have 6 separate laser beams arranged, so one from this direction and its partner from above, one from this direction and its partner, and then one kind of in this direction and one traveling this way. And so this means that we have a laser beam pushing the atoms in all 3 dimensions and both axes. And this is the first stage of what we will eventually do, which is to trap and cool atoms way colder than that, even to the state of matter known as Bose-Einstein condensate.
This magnetic optical trap, or MOT, means that you can hold onto these super cold atoms in the middle of a vacuum chamber like this, and keep them away from the sidewalls of your container so they don't touch it and instantly start to heat up. This is kind of hard to see happening because, well, it's a cloud of atoms, but also the laser is in the infrared, which our eyes and our cameras aren't very good at detecting. Here, my eyes and our main camera couldn't see anything, but when I put my phone in front of our camera, you can suddenly see a bright red dot. This is the trapped cloud of atoms. That's because the DSLR that we're shooting on had an IR filter over the top of it, meaning that we couldn't see any infrared, but our mobile phones didn't. The team helped make this slightly easier to understand by blocking and unblocking the line of the laser, which you can see on this screen with a special IR camera. The cloud of ultra-cold atoms spontaneously assembles and then kind of explodes as the trapping and confinement is turned off.
What's nice here is you can see as the atoms disappear, you can see them flying away because they're no longer held by the force of the trap, and they just expand ballistically into the volume of the vacuum chamber.
And yes, this does look like a blurry smudge on a screen, but that's quantum physics for you. It almost always looks like that. What was really impressive is how you can then make this atom cloud do something useful for you. To understand how this system works, we needed to get hands-on with the actual device.
Cool, heavy.
Valuable input, Ben. This device, to say the least, is reasonably complicated.
It's simple as long as you know quantum computing.
Yeah, as
That's
long
my
as you know
favourite
quantum
sentence.
computing.
Okay, great.
What we're looking at here is what we call the double MOT chamber, generates a 2D MOT. So this is similar to a 3D MOT, but we're confined in 2 dimensions. It's a line, cold atoms. We deliberately leave the 3rd dimension free. That's so we can introduce what we call a push beam. So that's another laser beam along the axis, and that imparts momentum onto the atoms in that axis, and they propagate up into the top chamber here. And so this is then when we do the 3-dimensional cooling, and then we can ramp those magnetic fields and the currents in the chip to load atoms into what we call the chip trap. The reason why we want to do that is because we want to generate the coldest state of matter, which is called a Bose-Einstein condensate. And what this is that if you keep on cooling atoms down, so we know the wavelength of the atoms is inversely proportional to the momentum. So the colder you go, the lower the momentum, the larger the wavelength. And so this nice thing starts happening where as you go colder and colder and colder, the atoms, the wavelengths start propagating out. And so when the wavelengths start matching the spacing between them, they turn into what's called a Bose-Einstein condensate, the coherent state of matter where all of the atoms are behaving in the same way.
You might have heard of the Pauli exclusion principle before, the idea that no 2 fermions or half-odd integer spin particles like electrons can be in the same place at the same time. This, however, doesn't apply for bosons, which have integer spin. When a collection of bosons, such as atoms like rubidium-87 or sodium-23, are cooled to temperatures close to absolute zero, their individual quantum states start to overlap. As the temperature decreases further, the bosons lose their individual identities, and a large fraction of them condense into the lowest energy state available, effectively behaving as a single super atom in a Bose-Einstein condensate. Here, quantum effects become apparent at the macroscopic scale. These condensates can exhibit properties such as superfluidity, where they can flow without any internal viscosity, and they can interfere with themselves like a wave, demonstrating wave-particle duality at the macroscopic level. It is this property that we want to make use of.
This is exactly what we want. We want to prepare a Bose-Einstein condensate, and then we want to do atom interferometry with it in order to detect motion with exquisite precision.
Interferometry looks at the interference pattern between two travelling waves. It is used in experiments you might have heard of before, like LIGO, to detect gravitational waves as they move through the Earth. Usually, interferometers interfere waves of light, but here we want to interfere waves of matter. This is kind of wild. I think we're all pretty familiar with light reflecting off of a material surface like a mirror, but it is reasonably rare that we see material reflecting off of a light surface. But that is exactly what is happening here.
Here we can see the atoms from above. So the black wires here are how we're going to run current through there, and that's going to create the trap. I'm going to shine a very powerful laser called a dipole laser from the side. Then I'm going to apply a coherent laser pulse, which will split this cloud into two. The atoms are going to move in opposite directions inside the dipole. Then we're going to coherently flip them back so that they recombine in the middle. And after completing this interferometry sequence, the phase of the atoms is sensitive to the acceleration. So we can take an image of the cloud and read out the portion of the cloud in each of the momentous state, and that will be a fingerprint of how the cloud was accelerating during the measurement. That image is destructive, so we will no longer have a Bose-Einstein condensate. The atoms will be warm and they'll be dispersed in the vacuum chamber, and therefore we have to start the whole cycle again. So we get one image every cycle, which is about once a second.
So what this technique relies on is that if there are any small changes to acceleration, the ship moving up, down, left, right, forwards or backwards, this will impart a small difference in the two clouds of atoms, such that when they are brought back together and recombined, you see a small interference signal correlating to this acceleration. Don't get me wrong, every single step of this process is incredibly difficult, and it would be an impressive feat if it was demonstrated just in the laboratory alone. But this is already far closer to reality, and back in May, the team flew this system on board a research flight to prove out its capability.
This is a video that we took in flight. Here we are, you can see the aircraft banking. And on the screen you see a single blob there, and that blob is a Bose-Einstein condensate being produced. In this particular video we're alternating between taking our BEC and then just imaging that directly, and taking the BEC and doing the first round of splitting that you'd need to do for interferometry. Whether you split or whether you just look at the BEC, you drop the atoms, they free fall briefly, and you do what's called absorption imaging, which is very simple. It's looking at the shadow the atoms create. And by looking at the relative density of these three blobs, you know the relative proportion of atoms in each of the three superposition states, and then you can back calculate what phase you would have accumulated, obviously due to an acceleration or rotation. The fact that you can even Bragg split a BEC in a plane and it's stable is remarkable. It's really, really amazing. And you can do so while the aircraft's moving around. You can see the clouds moving in the background.
To add some context as to why this is so impressive, the enemy of all quantum engineering is noise, both mechanical and electromagnetic. It's what we are fighting when we're building a quantum computer that makes it so hard to get right, and what the team here is having to overcome.
You know, you come from a physics lab where everything is bolted onto floating optical tables, and you know, the magnetic and the light environment and everything else is quite well shielded, to taking this on a really dynamically challenging environment like an aircraft, where the aircraft is shaking violently because of the engines. There is a 6 gigahertz weather radar at the front of the thing blasting. There's air traffic control. It's a very challenging environment.
We are finally getting to the point where quantum is becoming robust. The learnings that are here will map directly to other quantum technologies and open up applications that we never thought possible.
The challenge now is to show the performance and the capabilities of the quantum sensors in more of the deployed trials, and benchmark that against existing technologies and try to rapidly ascend that technology development curve. So lots of the existing technologies I mentioned before are plateauing in their performance. We're not going to get a 10x or 100x improvement in fiber optic gyros or ring laser gyros in the next few years. They've been very well engineered by lots of very smart people, but they're coming to the end of their development trajectory. We're just at the start of the development trajectory for quantum technologies.
The first generation of our products will be something that's rack-mounted system, something that can go into a data center or onto a ship or an aircraft. But ultimately where we're going longer term, and when I say longer term, this is really over the next few years, is to ruggedize and miniaturize these systems using, for example, photonic integrated circuits, so taking the lasers and the optics and the vapor cells that you've seen and printing these on silicon, so that ultimately these products will be something that could fit in the palm of your hand.
But positioning isn't the only problem that these systems could tackle.
So because the atoms are sensitive to acceleration, they are by the same exact principle sensitive to gravity. And so if we can measure gravity with exquisite precision, it enables us to, for example, understand where there are mineral deposits under the Earth. We can measure tunnels, we can measure geologic formations.
One day it may have applications from helping guide autonomous vehicles around high-rise cities or helping us to navigate space. But first it will be set to work to protect flights around the world, which as of 2024, 900 flights a day on average are now encountering GPS spoofing, a technology made possible by some of the most complicated but fundamental laws of our universe. Diving into these sorts of technologies is literally the coolest thing about what it is that I get to do as a factor of being on YouTube. If you liked this video, I'm going to leave some more kind of behind the scenes footage over on Patreon and post it here for channel members. Please do consider supporting us by joining or just by leaving a like or leaving a comment letting me know what other technologies you would like me to do a deep dive on. Thank you to Inflection and the team for letting me behind the scenes and letting me pick up the device before they told me how much it costs, which once I found out I promptly put it down again. And thank you, as always, for watching. I'll see you next week. Goodbye.